What you're looking at is the famous Big Dipper. By following the two pointer stars at the end of its cup, Dubhe and Merak, and extending that line upwards, your eyes will land on a particularly bright star. That is Polaris, the North Star. Polaris, located almost directly above the Earth's north celestial pole, has an apparent magnitude of about 1.98. If you can find the Big Dipper in the night sky, you can quickly find Polaris. For centuries, it has guided countless explorers navigating the Earth. However, if you study it closely, you'll discover that this star is actually a triple star system. Today, we'll journey into the world of Polaris to uncover the mysteries hidden within this famous star system. From Earth, Polaris appears to hover almost directly above our planet's axis of rotation. It stands like a steadfast sentinel, remaining fixed in place while other stars circle around it. If you live in the Arctic, Polaris is nearly directly overhead. As you travel south, it sinks lower in the sky, disappearing completely below the horizon once you reach the southern hemisphere. Since ancient times, humans have relied on Polaris to determine direction during ocean voyages and wilderness expeditions. But due to the wobble of Earth's axis, a process called axial precession, Polaris is not an eternal guide. A day will come when it will no longer be our North Star. But what many people don't know is that this star we trust so deeply holds far more complex secrets than we imagined. As early as 1779, astronomer William Herschel used his telescope to discover another star next to Polaris, naming it Polaris B. The main star became Polaris A. The two orbit each other in a very wide orbit. Then, in 1899, astronomer William Wallace Campbell noticed that the radial velocity of Polaris A was unstable. This suggested it had another, much closer companion. This companion star couldn't be seen with a telescope, and its existence was only confirmed by spectroscopic studies in 1929. It wasn't until January 2006, when astronomers pointed the Hubble Space Telescope at Polaris, that we saw the third star in the system for the first time. This close companion is now known as Polaris AB, while the main star is Polaris AA. This is a triple star system bound by gravity. The brightest star, Polaris A, is the one we commonly call the North Star. It is a yellow supergiant with about 5.4 times the mass of our Sun and is vastly larger. It forms a binary system with Polaris AB, completing one orbit every 29.6 years. The third star, Polaris B, orbits this pair at a great distance, taking about 40,000 years to complete one revolution. Astronomers have observed that Polaris B and Polaris A are both yellow dwarf stars similar to our Sun but fainter. Polaris B has a mass of 1.39 times our Sun, while Polaris AB is slightly smaller at 1.26 solar masses. But the most fascinating part of this system is its main star, Polaris A. It belongs to a very rare class of stars known as Cepheid variables. This identity is key to mapping our universe. In 1908, astronomer Henrietta Leavitt, working at the Harvard College Observatory, was studying the Small Magellanic Cloud. She focused on Cepheid variables, a type of star that pulsates rhythmically during its evolution, causing its brightness to change periodically. Leavitt discovered a direct relationship between a Cepheid's luminosity, its true brightness, and its pulsation period. The brighter the star, the longer its period. This was a monumental discovery. It gave astronomers a standard candle. This means if we can measure the pulsation period of a Cepheid, we can determine its true brightness. By comparing its true brightness to its apparent brightness, how bright it looks to us, we can calculate its distance. It's like knowing the true wattage of a light bulb. By seeing how dim it looks from a distance, you can estimate how far away it is. Before this, our methods for measuring cosmic distances were limited, primarily to stellar parallax, which only worked for objects within a few hundred light-years. With Cepheids, scientists could suddenly measure interstellar distances of millions of light years. We can now use parallax to calibrate the distances of nearby Cepheids and then use those Cepheids to measure the distances to other galaxies, building a cosmic distance ladder. This brings us back to a critical question. Just how far away is Polaris? We used to think Polaris was about 433 light-years away. In 2022, data from the Gaia Space Telescope revised this distance to 447.6 light-years. However, to the surprise of astronomers, Polaris A is a very misbehaved Cepheid variable. As the closest Cepheid to Earth, Polaris should be a goldmine for scientific research, helping us calibrate the size, age, and even the fate of the universe. From measuring the distance to the Andromeda Galaxy to studying the expansion rate of the cosmos, Polaris should be a crucial benchmark. The problem is that Polaris A's behavior is strange. First, its brightness amplitude, the change between its brightest and dimmest points, is unstable. From the 1960s to the 1990s, this amplitude steadily decreased. Then it stabilized for a while, but in the 2000s it began to increase again. This pattern is unheard of in other Cepheids. Second, astronomers have observed that its pulsation period has been changing abnormally for over 150 years. Its period is roughly 4 days, but it increases by about 4.5 seconds every year. For a Cepheid, this is an incredibly fast rate of change, as if Polaris is rushing through a phase of its evolution. Astronomers have a theory for this unusual behavior. Polaris A may be passing through a highly unstable phase of its life. All stars go through instability when they leave the main sequence, but not all become Cepheids. What type of pulsating star it becomes depends on its mass, luminosity, and period. Most Cepheids experience 3 major instability events, or crossings of the instability strip, in their lives. The first happens very quickly, perhaps in just 100,000 years, as the star stops fusing hydrogen in its core and evolves into a red giant or supergiant. Because this phase is so short, it's rarely studied. The second unstable phase occurs when the star begins burning helium in its core, becoming hotter and bluer. This can last 100,000 to 10 million years. When the star finally exhausts its core helium, it expands again, entering the third unstable phase. Most Cepheids we observe are in the second or third phase, so their behavior is relatively predictable. A Cepheid observed during the rare first crossing would be an exceptional find. The scientific community has not yet reached a consensus on which phase Polaris is in. Furthermore, Polaris will not always be our North Star. As mentioned, Earth's axis precesses, wobbles, in a cycle of about 25,800 years. During this cycle, the Earth's North Pole points to different stars. In about 14,000 years, Vega in the constellation Lyra will become the new North Star. For millennia, Polaris guided humans across oceans and deserts. Today, it guides us in a new way, forcing us to confront the complex physics of stars, galaxies, and the universe itself. The next data release from the Gaia Space Telescope is expected in 2026. Perhaps one day we will finally unravel all the mysteries of Polaris, elevating our understanding of the cosmos to a new level.